Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everybody. How's everybody doing today?
Good. How are you, Professor?
Good, good. Yeah, it's
Doing
chilly.
well, Professor.
Wait, say it again?
Doing well.
It's good, that's good. Yeah, it's chilly. It was, I feel like I got the best night's sleep last night than I have in a while because it's so much easier to sleep when it's cool like this. You can really just bundle up under the blanket. So it's good. Okay. So the plan for today is we're going to keep continuing on with our lecture notes on isoparametric elements. So my goal today is to basically finish enough information so that you can finish doing the homework. And so with the, after today, you should be able to do problem 3D, which is on Gauss quadrature, which there was another typo on. I need to update the PDF on that. And also on problem 4B. So after today, you should be able to do all of them. Right? Okay. So that's the plan for today. Another announcement I want to make is Wednesday is going to be a holiday. So Wednesday is Veterans Day. And so we're not going to have lecture on Wednesday. And so you know, I'll still be here. So you know, I'll be here if you want to chat about the homework or you want to chat about the project. You know, just shoot me an email and then we can set up a Zoom call because I'll be free basically all day on Wednesday. But we're not going to have lecture on Wednesday. So after today, the next lecture that we're going to have is next Monday. Okay. Okay. So are there any questions I can that I can answer before we get started today? Midterm is next Wednesday, correct? Yes. Mm-hmm. Oh, yes. So since this is the last time that we'll meet until next Monday, I'm going to do the same thing I did last time with the review session. So probably over the weekend because this week's is actually going to be really busy for me. But over the weekend, I'm going to film a review session, or like a review video, I guess, for basically everything that we've covered since the first midterm. So and so what I'm going to do at the end of the week is I'm going to put up a poll on Canvas where you can vote on the topics that you'd like to see on the review video. Okay. And so based on the results of the poll, I'll probably cover the top 2 topics on there and record about an hour-long video that'll be a review of that. And so just keep a lookout for that, you know, and I'll post a study guide for that as well, just so that to kind of help you on with the with your study. Okay. Okay. So my Zoom crashed on my iPad. Yep.
For the midterm, are we going to need to use the MATLAB?
My plan is right now is to no, and so you can use MATLAB just the same as last time to help you compute the element stiffness matrices, but you know you're not going to have to implement any MATLAB code. So it's not going to be anything like the what's it called, the 1D boundary value code, but you can use it to just help you just solve a linear system or stuff like that. So it'll be like a complementary tool, but not a necessary one for the midterm. Yeah. Mm-hmm. All right, so the question is, up until today's lecture, starting from weak form, are covered for the midterm. Yeah, so it's going to be starting at strong. So the first lecture that's going to be on the midterm is going to be the one on strong form, and it's going to be everything up until today. So basically, you know, if you kind of remember, at the very first half of the class, we did, you know, up to frame equations, and then right after frame equations is going to be on, you know, we started with strong form. So everything from strong forms up until today is going to be covered on the midterm. Yeah. Mm-hmm. Okay, but I'll put out a study guide so that you guys will be able to know what to study for the exam. Okay. Okay. Are there any more questions before we get started? Okay. Okay. And so we're going to continue on. And so remember from last time we were talking about isoparametric elements. Okay. And remember the whole idea with isoparametric elements was that they you know, they're elements that are formulated on like a standard domain, or we call it a parametric domain, that makes it easier to evaluate integrals. Okay. Okay. And so, you know, we were kind of motivated by the fact that, you know, just by the idea of this of Gauss quadrature, which will help us evaluate the integrals. Okay. Okay. And so last time what we were covering was this isoparametric 4-node quadrilateral. Okay, so like the isoparametric form for a rectangular element. Okay? And so it looks something like this. Right. And so remember, when we're in the isoparametric space, we switch the coordinate terms. So instead of x and y, what we have is xi and eta. Okay. And so this is node 1, this is node 2, this is node 3, this is node 4. Okay. And the coordinates for these coordinates are given by -1, -1. We have 1, -1, 1, comma 1, and then -1, comma 1. Okay. And so where we left off last time was we talked about, you know, the shape functions. Okay. And so there's going to be 4 of them because we have 4 nodes here. Okay. Excuse me. And so those are our shape function, you know, expressions. And then in addition to that, we also have the shape function derivatives. Okay. So the derivatives are going to be really important because they help us compute, you know, things that are going to go into our matrix. Okay. Right. And so we actually had 8 derivatives, right? So we have to take derivatives of each of our 4 shape functions. We have 4 of them here. And then we have to take derivatives in both psi and in the eta directions. Okay. So I'm not going to write out their expressions again, but you know that's kind of just what we started from last time. Okay? You know, and I didn't pull these shape functions out of thin air. So if you remember from when we covered the 4-node quadrilateral, you know, we looked at the shape functions for something like that. So all I did for that one was I plugged in the special, you know, coordinates for these, where the coordinates are you know, given by 1 or -1, and that's how we got the shape function values and the shape function derivatives. All right, so what we're going to do today is we're basically going to see how we can actually use this information or use these tools in order to set up this integral. Okay. Okay. Any questions so far on just very quick review of what we covered last time? Okay. Okay. And so in addition to those shape functions, remember what we can do is we can use those shape functions to interpolate any quantity that we want, okay? And in particular, what we can interpolate is we can interpolate the nodal coordinates, okay? All right? And so just like we saw in the 1D case, we can make a function of x, and this is going to be the x coordinate as a function of our isoparametric coordinates. Okay? So it's going to be x as a function of xi and eta, right? And the way that we form this is we take the x coordinate of each of the nodes, and then we multiply them by the corresponding shape functions. Okay? And we can do the same thing for y. Okay. All right. And so what we can do from here is that now that we have these functions of, you know, this x function and this y function, we can take derivatives of these with respect to eta and xi. Okay. Okay. And so let me write out those expressions here. Okay. So first we have dx d psi. Okay. And so we're just going to take the derivative of the top expression with respect to xi. And so we have x1 dn1 d psi, okay, plus x2 dn2 d xi, okay, x3 dn3 d xi plus x4 dn4 d xi. Okay. All right. So similarly, we can take the derivative of x with respect to eta. Okay. So you have partial x, partial eta, and so this is x1 dn1 d eta plus x2 dn2 d eta plus x3 dn3 d eta plus x4 dn4 d eta. Okay. Right. And we can find similar expressions for dy d xi and also dy d eta. Okay. So I'm not going to write out those full expressions just because they're a little bit lengthy, but you kind of get the idea with that. Okay. Okay. And so why are we doing this? So the reason we're doing this is because these functions right here are these derivatives. Okay. These derivatives are going to form key components of our mapping. Okay. Because remember, in order to use our Gaussian quadrature, we're going from an element that's oriented in kind of arbitrary physical space into the element in the parametric space. Okay? And so in order to do this, we need to be able to map in between the two spaces. Okay. In particular, we're going to summarize these into kind of one term, which is known as the Jacobian matrix. Okay. And so I'll write out what the expression for the Jacobian matrix is on the next page. Okay. All right. Any questions on this before I turn the page? Okay. Okay, so let's write out the expression for the Jacobian matrix. Okay, so the Jacobian matrix is going to be given by the symbol J. Okay, and I'll put square brackets around it just to denote that it's a matrix, right? And so the Jacobian matrix is going to be partial x, partial xi, and then we have partial y, partial xi. We have partial x, partial eta, and then partial y, partial eta. Okay. And so, you know, this matrix is going to be really important. Okay. And what this matrix is used for is it's used to convert the bounds of our integration. Okay. Okay. All right. And so basically it's used like this. So let's say that we have an integral in the physical space. Okay. And so we have double integral of f dx dy. Okay. And so this integral right here is in the physical space. Okay. We don't want to evaluate that integral because it's, you know, it's going to be a pain to do in the physical space. And so what we can do instead is we can evaluate this on our parametric domain. Okay. And remember, our parametric domain is nice because our integration bounds here are going to be from -1 to 1 on both, in this case, xi and eta. Okay. Okay. And so this is nice, right? Because this integral right here we can evaluate with Gauss quadrature. Okay. But we can't just simply, you know, change the integration bounds like that. We have to add like a scale factor. Okay. And that scale factor is actually given by, you know, this Jacobian here. Okay. So in particular, the scale factor is going to be the determinant of the Jacobian. Okay. And so by taking the determinant of the Jacobian, this basically allows us to transform our integration bounds from the physical space, which might be something crazy because we might have an arbitrarily oriented element, and it's something that's a lot simpler that we can do for the in the parametric space. Okay. Right. And so this process right here is actually really analogous to what we did to transform our 1D integrals. Okay. So remember when we did 1D Gauss quadrature, in order to transform the bounds, we had to add that additional factor. Okay. And so this is basically the same thing as what we did in 1D, except now it's kind of extrapolated to 2D. Okay. Any questions on this? Okay. All right, so just to kind of show you, what it was like for the 1D case. Remember, for the 1D case, we had to do our change of variables. Okay? Okay. And so remember, for 1D integrals, maybe we had an integral of f dx. Okay. And so in order to change this into, the Gauss quadrature domain, okay, right, where our integration bounds are -1 to 1, right? Remember, we had to add this additional factor right here of dx d xi. Okay. Just to make sure that our change of coordinates was valid. Okay. And so the determinant of the Jacobian is basically the exact same. It's the exact same thing. Okay. Okay. And so in addition to the Jacobian, another quantity that's going to be important actually is going to be the inverse of the Jacobian. Okay. And so this usually has the symbol of j to the -1, okay, to indicate inverse. Okay. And the way we obtained it is we just, you literally just take the expression that we had before, and we just take the inverse. Okay. So most of the times you're going to rely on like MATLAB to do this for you, because even inverting a 2x2 matrix can be kind of a pain in the ass. So, definitely use your computer programs, but what's going to be important here is going to be more the interpretation of the terms here, because we're going to use that in kind of our derivations from here on out. Okay. And so if we take the inverse of this, you can almost think of it as we take every term in this matrix and we kind of flip it on its other side, but we're also going to transpose the matrix. So that's generally what happens when you inverse. Okay? And so kind of the variable expressions for this inverse would be d psi dx, okay? Then we have d eta dx, right? Then we have dy d psi dy, sorry. And then d eta dy. Okay? And so when we take the inverse of the Jacobian matrix, the 2x2 matrix that results, the way that we can interpret the terms are going to look like this. So it looks like kind of the inverse of our positional derivatives that we took before. Okay? And this is going to be really important really soon, because what this is going to do is it's going to allow us to transform some of the derivative terms in our element stiffness matrix. Okay. Okay. Any questions on this? Yeah.
Oh yeah, I have a question. Why is it 1D, the integral? Because I thought we were just working in 2D, right?
Right. Yeah. So this is kind of just an analogy. So the expression that I had on back here, with the determinant of the Jacobian, this is in 2D. But I was just showing you that the reason we include that determinant of Jacobian is exactly the same. The reasoning is exactly the same reason why we included this guy right here. So when we did 1D Gauss quadrature, one of the requirements was we had to include this guy just to make sure our change of coordinates was working out okay. And
but
so,
the scaling factor is different for 2D. It's not like d of x over d of xi, right? It's like
exactly.
a different thing.
Exactly.
Oh,
right. Yeah, because in 2D we have 2 dimensions now, so we need to kind of account for that. And the way that we account for those 2 dimensions, we have this this matrix right here. Yeah. And by taking the determinant, that's kind of the same thing as that.
Get it. Thank you.
Yep. Okay. Any other questions on this? Okay. Okay. And so how is this used? Okay. And so let's kind of take a step back for a minute and kind of remember, you know, the expression for our element stiffness matrix for a 4-node quadrilateral. Okay. Let's call it a rectangle. Okay, so remember in 2D, you know, our element stiffness matrix looks like this. So it's going to be the double integral of the gradient of W, okay, times K times the gradient of T, okay, dA, okay, where this gradient of W here was given by the following expression. And so we had W1, W2, W3, W4, okay? And then we had our shape function derivatives here. So we have partial n1, partial x, partial n1, partial y, partial n2, partial x, partial n2, partial y, partial n3, partial x, partial n3, partial y, partial n4, partial x, and partial n4, partial y. Okay. And so the gradient of t had a similar expression. Okay. So gradient of t was equal to partial n1, partial x, partial n1, partial y, partial n2, partial x, partial n2, partial y, partial n3, partial x, partial n3, partial y, partial n4, partial x, partial n4, partial y, okay? And then in front right here, we have our column vector of T1, T2, T3, T4, okay? Okay? And so the important thing that I want to highlight here is the fact that we have all these shape function integrals, or shape function derivatives right here, okay? Okay. And so the problem with this is that, you know, these shape function derivatives, they're taken with respect to the physical coordinates, okay? Okay. Notice the derivatives are in x and y instead of xi and eta, okay? And so this is a problem because, you know, we don't know what the shape function derivatives in the physical coordinates are. What we do have is we have the shape function derivatives in the parametric coordinates, okay? Okay. But those shape function derivatives in the parametric coordinates, we actually can't use them to plug in here yet, okay? And so we actually need to work on them a little bit just to make sure that, you know, we get our shape function derivatives in the physical coordinates, okay? And we'll do that on the next page. Okay, so before I get there, are there any questions on this? Okay. Okay. And so what we need, so kind of the dilemma that we have right now is we have these shape function derivatives in the physical coordinates, right? And so let's just take dn1 dx, right? And so this is something that we need to plug into our integral in order to evaluate the element stiffness, okay? But we don't have this right now. Okay. And what we have instead is we have the derivatives of the shape functions in the parametric coordinates, okay? Okay. And so in the parametric coordinates, we have the derivative of n1 with respect to xi, and then we also have the derivative of n1 with respect to eta. Okay? And so these guys we do have. Okay. And so in order to kind of convert, you can kind of almost think of this as converting these into a physical derivative. What we need to do is we need to multiply both of these shape function derivatives in green by a conversion factor. Okay. And so you can almost think of this as kind of stoichiometry a little bit. Okay? And so what we're going to be doing is we're going to be multiplying by partial derivatives of the parametric coordinates with respect to the physical coordinates. Okay. And so you can almost think of this as you know, if we want to convert this dn1 d8 to dxi into dn1 dx, then we have to multiply by dxi dx, so that these two xi's cancel out just like that. Okay. It's not exactly algebraic like that, so you can't you know, it's not exactly like that, but that's the same idea. So you know, we have an expression for dn1 dxi, and we actually also have expressions for these guys in the purple right here too. Okay. And so by multiplying them together and then adding them together like this, then this gives us our physical shape function, our shape derivatives of the shape functions in the physical coordinates. Okay. Right. And so by kind of doing this almost like a reverse chain rule, or this is actually chain rule, you know, we can actually, you know, get the things that we need. Okay. And so what are these terms in purple? So these terms in purple right here, these are the terms in our inverse Jacobian. Okay. Because remember, the inverse Jacobian had the derivatives of each of our parametric shape functions or parametric parameters with respect to the physical parameters. Okay. And so just for completeness, I can also write out, you know, dn1 dy. Okay. And so this has a similar expression. So in green, we can have the derivatives of the parametric shape functions. Okay. Right. And then in purple, we can write kind of the chain rule terms. Okay. So this is going to be d xi dy. This can be d eta dy. Okay. And so just like in above, these purple terms are going to come from the inverse Jacobian. Okay. And the green ones we can calculate. So the green ones are kind of what we wrote down last time. Okay. And so we can use this information. So we can use the fact that, you know, the fact that we have the inverse Jacobian and the fact that we have the shape functions in the parametric space, we can kind of multiply these two matrices together in order to get the shape functions in the physical space. Shape function derivatives in the physical space. Okay. Right. And so let me see. It's going to be a little bit long to write down here, but let me try. Okay. And so as an example, let me write down the term that you would use for W right here. Okay. Right. And so for that W, that gradient of W, what we want is this matrix right here. So we have dn1 dx, dn1 dy, dn2 dx, dn2 dy, okay. dn3 dx, dn3 dy, dn4 dx, dn4 dy. Okay. Right. And so this is going to be equal to our inverse Jacobian. And so our inverse Jacobian is given by d xi dx, and then d eta dx. Okay. Let me write this a little bit more cleanly. Okay. Then we have d xi dy, and then d eta dy. Okay. And so this right here is our inverse Jacobian. Right. And then to this, we're going to multiply a matrix of our parametric shape functions. Okay. So we have dn1 d xi, dn1 d eta. Okay. this, just so I'll have a bit more room. Okay, so dn1 z xi, okay. dn2 d xi, dn2 d eta, dn3 d xi, dn3 d eta, dn4 d xi, dn4 d eta. Okay. And so this matrix right here is contains all of the parametric shape function derivatives. Okay. Okay. And so everything on the right-hand side of this equal sign, you know, we already have expressions for these that we've kind of already talked about before. Okay. And so by multiplying these two matrices together, you know, we can basically form the expression that we need to. Okay. Right. So actually, this is I wrote this a little bit backwards. So this should be, there should be a transpose right here. Okay. And so basically, you know, we can use these the inverse Jacobian and also the parametric shape function derivatives in order to form both of these matrices right here that we have in red. Okay. And so in red, I have basically the physical shape function derivatives in kind of as a row, kind of as a long matrix. And in the bottom one right here, I have the shape function derivatives as kind of a column matrix. Okay. And so you can basically, you know, use some matrix algebra and kind of use the inverse Jacobian and the parametric shape function derivatives in order to get these expressions. Okay. Okay. And so if we do that, we can and we put it all together, we can get an expression for the element stiffness matrix using parametric shape function derivatives. Okay. And I'll do that on the next page. Okay. And so before I do that, are there any questions on this?
I got a little bit confused. So is the this one is the W, and then the second one is like the T, like a gradient of W and the gradient of T. Are they the same thing?
So the grade, right? So they use the same shape functions, right? So that was kind of the assumptions that one of the assumptions that we made when we started with finite elements is that, you know, the weighting functions and our solution functions, they have the same, you know, shape functions. And so by taking the gradient of them, right? And so by taking this this nabla operator to those variables, you know, what we end up with is kind of the same matrix, almost the same matrix on both sides, where we have the derivatives of our shape functions, which is going to be the same for both of them. It's just that they're in different forms here. You know, one is kind of in a long form, and the other is kind of in a tall form. Just to make sure that we can end up with in this case, a 4x4 element stiffness matrix.
But by inverse, like multiplying by the inverse of Jacobian, it can like turn one to the other, right?
So it's by multiplying by the inverse Jacobian, what we're doing is we're transforming the derivatives here. So you can see on the right here we have derivatives in the parametric coordinates, which is in xi and eta, and then we transform them into derivatives of the physical coordinates, which is x and y. Yeah.
Got it right now. Sorry. Yeah, I made a mistake. Thanks.
Yep. Yeah, so remember the Jacobian, the main role of the Jacobian is to help us transform between the coordinates, right? And so on one side we have x, y coordinates, on the other side we have xi and eta coordinates. And so whenever we kind of transform in between them, usually the Jacobian is involved in some way. So either the determinant of the Jacobian, but in this case it's the inverse of the Jacobian. So that's kind of the main purpose of that. Yeah.
Get it now, thank you.
Yep. Mm-hmm. All right, any other questions on this? Okay, and so let's finalize our expression for the element stiffness matrix, or at least let's try with kind of the limited space that I have to write. Okay, and so our element stiffness matrix is given by, and so we have a double integral here. Okay. Right, and so first we have this kind of a tall matrix with our shape function derivatives in the parametric space. Okay. I said parametric space, and I started writing physical derivatives. Okay. And so those are our derivatives of the shape functions in the parametric space. Okay. To this, we're going to multiply by our Jacobian inverse. Okay. In order to transform this into, derivatives in the physical space. Okay. And so this product right here is going to be our, matrix of shape function derivatives in the physical space. Okay. Okay. All right. And so to this, we're going to multiply by k. Okay. So we can't forget k. Okay. Then we have our Jacobian inverse again. Okay. And then to this, we're going to multiply by the same thing here, but transposed. Okay. Okay. And so we have partial n1, partial eta, partial n2, or partial n1, sorry, partial eta, partial n2, partial xi, partial n2, partial eta, partial n3, partial xi, partial n3, partial eta, partial n4, partial xi, partial n4, partial eta. Okay. And so same thing right here. This this guy right here is the product of these two is going to be the shape function derivatives in the physical space. Okay. And so this integral right here, this kind of massive guy, this is our element stiffness matrix. And so not pictured here, remember, is going to be our weighting function coefficients. Okay. So in front right here is going to be, W1, W2, W3, W4. Okay. And then over here, what we have is T1, T2, T3, T4. Okay. And so those guys couldn't fit, so that's why I kind of put them over there. Okay. And there's actually one more guy that's not included here that, remember, we need to include. Is we also need to include the determinant of the Jacobian in order to make sure that that our our computations are good. Okay. Our integration bounds are successfully converted. Right. Okay. And so obviously, I would never ask you to compute something like this by hand, except in some special cases. Okay. And so 99% of the time, you're going to ask the computer to do these calculations, just because computer can do this kind of matrix multiplication. It can do the matrix inverse really quickly, and so you don't have to do these by hands. But I wanted to give you the expression just because it's first of all you're gonna do this for the project, and second of all this is kind of what's under the hood for all the finite element codes. Okay. Any questions on this?
Professor?
Yep.
We have here two Jacobian inverse because we need to transform both of the matrices to X and Y. That's right?
Exactly. Correct. Yes. Yes.
Thank you.
Mm-hmm. Yeah. So that's a good observation. So you need two Jacobian inverses, and you also need the determinant of Jacobian. And so they play different roles here. So the Jacobian inverses here, what their role is to make sure that we transform the derivatives of our shape functions into the physical coordinates. Okay. And then the determinant of the Jacobian, that one's role is to transform our integration bounds to make sure they go from -1 to 1. Okay. And so you have to include basically all the Jacobians here, just to make sure that everything is transformed properly for this integral. Okay.
Professor?
Yep.
To compute that, are we going to do it in MATLAB?
Yeah. Yeah, so you're going to compute these guys in MATLAB just because it's just not practical to do these by hand, because it's, first of all, matrix inverses are a pain in the butt to do by hand, but also just all the matrix multiplication, like this is way too much to do by hand. So you would have to do this with MATLAB or any other programming language. Yes. Yeah, so the lecture notes, they show a determinant of J and the two inverse Jacobians as well. Yeah. Mhm. Okay. All right, so that's the element stiffness matrix. And so now let's kind of briefly go over the element forcing vector, okay? Okay. And so the element forcing vector for a quadrilateral is given by this, okay? And so we have the integral of n1, n2, n3, n4, okay? And so remember, this is a line integral because this is for our Neumann boundary condition, okay? ds plus the integral of our thermal generation term, okay? So we have n1, n2, n3, n4, okay? And this is times s of x and y dA. Okay. All right. And so just like we did with the element stiffness matrix, you know, we need to transform these guys into the parametric coordinates. Okay. Luckily, these guys are a lot simpler because these don't involve any derivatives of the shape functions. Okay. So let's start with this one. Okay. And so for the thermal generation integral, the only thing we have to do is just transform the integration bounds. Okay. And so the only one that we're going to see here is just the determinant of the Jacobian, okay? And so the proper transformation of this would be double integral of n1, and this is now functions of xi and eta, okay? Okay. Then we have s, which is now also a function of xi and eta, okay? Then we have our determinant of Jacobian, because remember, we're transforming the integration bounds, and it's going to be d xi d eta, okay? And so by doing that, we can transform integration bounds to -1 to 1, okay? Okay. And so that one's pretty simple. So basically all we have to do is just multiply by the determinant of Jacobian and just make sure that we express our s of x and our shape functions in terms of the parametric coordinates, okay? And so we're going to do an example later just to kind of, you know, show how this is. And so now let's talk about the Neumann boundary condition term, because this one's a little bit more complicated. Okay? So before I do that, are there any questions on this page? Okay. All right. So the Neumann boundary condition term is a little bit interesting because instead of doing a double integral, you can see here that we have to do a line integral. Okay. And so what we're actually going to use, since a line integral is simply just a 1D integral, we're going to use instead of a 2D Gauss quadrature, we're going to use a 1D Gauss quadrature. Okay. And so this integral, basically, of n1, n2, n3, n4, okay, of q bar ds, okay, is going to be equal to integral of n1, n2, n3, n4, where all of these guys are functions of xi and eta now, okay? And so we have our q bar, okay? But now we have to multiply by the length of the edge divided by 2, okay? And so this basically is our kind of our scale factor from from transforming this integral. Okay? Okay. And so I don't want to get too much into this right now, just because it's, you know, I want to make sure that you guys have enough to do the homework. But basically, you know, in order to evaluate this integral right here, we need to eliminate one of the variables, okay? Because remember, this integral right here is only an integral in one variable, okay? But right now we have both xi and eta, okay? And so what you need to do in order to evaluate this integral is to kind of look at your element here and to say, you know, which one is, you know, which edge on this element is our Neumann boundary condition going to be applied. And so depending on what edge that you're on, you can basically plug in either 1 or -1 for eta and or xi, okay? And so let's say that, you know, our Neumann boundary condition is going to be on this side of the square right here, okay? And so if it's on this side, you know, we're basically going to be integrating up this side like that, okay? And then for the entire length of this side, then we can set, xi is equal to 1, okay? And so by doing that, we can evaluate this integral just because, you know, we'll have eliminated xi, and so we're just going to be integrating in eta, okay? And so evaluating the Neumann boundary conditions are actually going to be pretty tricky. So that's also kind of why I left it from last, you know, for the project. And so when you evaluate these Neumann boundary conditions, you know, you need to be able to determine which edge on your element, you know, has the Neumann boundary condition, so that you can perform the appropriate, you know, simplifications of your shape functions in order to perform that integral. Okay? And so this is one of those things where it's actually easier to do it by hand because, or it's easier to kind of visualize by hand because you can kind of visually see the element and you can see, you know, this edge right here, that's where we're going to apply the Neumann boundary condition. And so this is how we need to simplify that. But coding it is a little bit, you know, you have to jump through some hoops a little bit. And so I try my best to kind of walk you through it, but it's still going to be a little bit, you know, I think that's probably going to be the hardest part of the project. Okay. Okay. But at least doing it by hand, you know, I hope to finish an example by the end of class today. Okay. So before we get on with that, are there any questions on this? Okay. All right. And so that's all the theory that kind of goes into this. So let's talk, you know, how do we actually do this by hand? Okay. And so what I'm going to do next is I'm going to basically give you the recipe or the algorithm for Gauss quadrature on a 4-node rectangle. Okay. Okay. And so let's draw our rectangle here. Okay. And so for a 2D Gauss quadrature on a rectangle like this, you know, we have options. Okay. And our options are going to be determined by how many Gauss points that we want. Okay. And so you have the 1-point rule. Okay. And so the 1-point rule is pretty convenient. So all we have to do is evaluate the integrand at the center of our rectangle. Okay. But what's more common is going to be the 4-point rule. Okay. Okay. And so the coordinates for this are going to be 0, 0. And the coordinates for these are going to be, you know, different powers of, you know, 1 over square root 3. And so that's 1 over square root 3, 1 over square root 3. And this has a minus sign in the eta component. Okay. And so I'm going to give you an algorithm that will basically solve it for kind of both of these cases, okay? But the reason I'm giving you both here is because the homework is going to ask you for both, okay? So I think in problem 3, you know, I asked you to do a 4-point rule, but in problem 4, because, you know, there's a lot more calculations, I said, you know, just use a 1-point rule. But this algorithm kind of works for both, okay? Okay, and so the algorithm starts like this, okay? And so it's going to be written in kind of like pseudocode. So it's I'm going to use kind of a for loop right here. Okay? And so to evaluate this Gauss quadrature, you have to write a for loop for each of the quadrature points. Okay? Okay. And so if we're doing a 1-point rule, you know, our loop is just going to go once. But if we're doing a 4-point rule, you know, our loop's going to go 4 times. Okay. Okay. And so step 1 of the algorithm is to establish the parametric coordinates at the Gauss points. Okay. And so these will be given, or the way that we'll denote these is we'll call it xi g and also eta g. Okay. And so, for example, let's say that we're going to, you know, evaluate the Gauss point or evaluate the coordinates at this node right here that I've circled in red in blue. Okay. And so for that node right there, then we say xi g is going to be -1 over square root 3, and then eta g is going to be -1 over square root 3, okay? Because those are the coordinates for that point right there. Okay. All right. Any questions on this so far? Okay. Okay. And so step 2, what we want to do is now that we have the parametric coordinates at the Gauss points, is now we need to calculate the shape functions at this point. Okay? Okay. And so remember, we have 4 of them. Okay. And so all you're going to do is plug in the you know, the values for xi g and eta g, okay, into all these expressions. Okay. Okay. And so, you know, we have the formulas for these shape functions, you know, that we went over last time. So all you got to do is just kind of plug in, you know, the coordinates for the Gauss point. Okay. All right. Right. So the next step is we need to compute the shape function derivatives at the Gauss points. Okay. And so there's going to be 8 of these, and so, you know, they're going to be dn1 d xi, dn1 d eta, okay, dn2 d xi, dn3 or dn2 d eta, sorry, dn3 d xi, dn3 d eta, dn4 d xi, and dn4 d eta. Okay. And so we need to evaluate these at xi g and eta g. Okay. Right. And so in addition to that, we can actually put these, into a matrix, which is going to help us out later too. Okay. And so in fact, the matrix actually looks just like this. Okay. And so this matrix right here is going to be a 2 by 4. Okay. And it has all the shape function derivatives with respect to the parametric coordinates. Okay. And so all we've done up to this point is that, after we've established, the coordinates of our Gauss point, and so, let's say in this case, it's -1 over √3, -1 over √3, all we've done so far is just computed or evaluated the values for the shape functions and the shape function derivatives at these Gauss points. Okay. And so this is all just set up so far. So, we're gonna use all this information, in a little bit, but in order for us to do any of the other calculations, we need to do these first, and then kind of store them into matrices that we can use them in a little bit. Okay. All right. Any questions on this? Okay. Okay. And so the next step is we need to compute the physical coordinates at the Gauss points. Okay. Okay. And so this is kind of the equivalent of, if we go back to our code that we worked on together, this is going to be the same thing as like XGP1, right? And so remember, XGP1 was the value of X at the Gauss points. Okay? And so XG in this case is going to be X1 multiplied by the shape functions at the Gauss points. Okay. And so remember, we computed the shape function values, we computed these in an earlier step. So we did all of these in step 2. So we have all of these already. And so the next thing is we just have to pull in the spatial coordinates and then multiply them by the corresponding shape functions. Okay. And so we can do basically the same thing for YG right here. Okay. And so for YG, it has the same expression. It's just that we replace all the X's with the Y's. Okay. And so now that we have the XG and YG, we can basically compute the Jacobians. Okay. Okay. All right. And so computing the Jacobians is, just it's going to be a simple matter of just kind of multiplying these two matrices together. Okay. Right. So the first matrix is going to be our shape function derivatives in the parametric coordinates. Okay. Okay. And so I'm just going to shorthand it because it's a lot to write. So, but this is the shape function derivatives in the parametric coordinates. Okay. And so this was step 3. Okay. So those are all the ones that we compute in step 3. Right? And then to this, we're going to multiply by a matrix of the physical nodal coordinates. Okay. Okay. And so if we do this, then we get our Jacobian matrix, which is dx d xi dx, d eta, dx, or sorry, dy d xi, and dy d eta. Okay. Right. And so once you have the Jacobian matrix, you can basically use the code to compute two other things. Okay. And so you can also use this compute J inverse. Okay. And you can also use it to compute the determinant as well. Okay. And so all of that information just can come from step 5 right there. So step 5 is really important because these Jacobian things we're going to we're going to use. Okay. Any questions on this so far? Okay. Okay. And so in step 6, what we're going to do is we're going to compute the shape function derivatives in the physical space. Okay. All right. And so I'm going to call this matrix B, okay? Or in other words, B sub G, okay? And so just like we saw before, this is going to be the product of J inverse, okay, multiplied by our shape function derivatives in the parametric space, okay? And so this can be partial Ni partial xi j, okay? And so just like in the previous slide, this is going to be our shape function derivatives in the parametric space. Okay. And so, by multiplying these two guys, this is what we get. We get BG, where BG is our shape function derivatives in the physical space evaluated at our Gauss points. Okay. All right. And so the last thing that we need to do before we exit the loop is we need to, if we have a heat generation term, is we need to compute the value of that heat generation at the Gauss points. Okay. And so from that we have we'll call it SG, and we'll say this is S of XG comma YG. And remember, we computed XG and YG back in step 4. Okay. Okay. And this is something that we're going to need as well. Okay. Okay. So I know it's a lot of steps, but a lot of it is kind of set up. And once you've set up the matrices, then all you have to do is just kind of multiply them together in order to get a lot of these quantities. But it's a lot of setup just because it's you have to set up the shape function matrix and the shape function derivatives. But once you got it going, then it's just a lot of multiplication. Okay. And again, most of the time you're going to set this up in code to do this for you because it's it's way too many calculations to run by hand. Okay. Okay, any questions on this? Okay. Okay, and so by step 7, all your calculations are complete. But in order to make sure that we can actually complete the Gauss quadrature, we need to make sure that we save the appropriate variables. Okay. And so here's the variables that we need. Right. So the first one that we're going to need is B sub G. Okay. So remember, B sub G here is the shape function derivatives in the physical space. Okay. next thing we need is the determinant of Jacobian at the Gauss points, okay? And so we'll call that determinant of J at G. Okay. Right. Next thing we'll need is the shape functions themselves evaluated at the Gauss points. So we'll call that NG. Okay. And then the last thing that we need is the value of the heat source or the heat generation term at the Gauss points. So we'll call that S sub G. Okay. Okay. And so, that was just for one loop iteration. And so, you're going to do this for every single Gauss point. So, you're going to repeat this kind of 4 different times if you're using a 4 Gauss point loop. Okay. And so once you're done with this loop, then you have everything you need to compute the Gauss quadrature. Okay. All right. Okay. And so just as an example, the way that we compute KE is that we're going to basically sum up from G is equal to 1 into the number of Gauss points. And so this is going to be either 1 or 4. Okay. Then to this, we're going to basically take the sum of BG transpose times K times BG times determinant of J at G times WG. Okay. Remember, this WG here is the Gauss weight. Right. And so that's the expression for the element stiffness matrix. Okay. And then the element forcing vector, at least with regards to the forcing term, with the heat generation term, looks like the following. Okay. And so FE is going to be the summation of G is equal to 1 to M of NG transpose times SG times determinant of J, G, okay, times WG. Okay. Right. And so that's how we compute the element forcing vector with Gauss quadrature, given everything that we've computed up to this point. Okay. Okay. And so I'm going to hold off on how to solve the Neumann boundary condition term, because I want to make sure I at least cover some of this example, because this example is pretty relevant for the homework. Okay. Okay. But before we jump into that example, are there any questions on this algorithm here? Okay. All right. And so in this example, let's consider the following element. So our element kind of looks like a trapezoid here. Okay. And so we'll number the elements, number the nodes, 1, 2, 3, and 4. Okay. Let's say that we have a thermal generation given by 20x plus 10y. Okay. Our K here is going to be a constant, 10 watts per meter K. Right. And let's write out the coordinates for all the nodes. So node 1 here is going to be at 0, 0. Node 2 right here is going to be at 1, 0.2. Node 3 right here is going to be at 0.8, 1. And node 4 is going to be at 0.2, 0.9. Okay. Okay. And so, another thing that's going to be there, which we'll probably do on another day, is there is a Neumann boundary condition here. And so the Neumann boundary condition is given by 5 watts per meter squared. Okay. But we'll do that another day. But what I want to do first is I want to, let's use isoparametric elements and Gauss quadrature to compute the element stiffness matrix and element forcing vector. Okay. And so in fact, let's use a 4-point Gauss rule. Okay. But I'm only going to do the calculations for one Gauss point because it's already kind of a lot from that. Okay. Okay. And so let's follow the same algorithm that we followed from before. Okay. Okay. And so step one of this algorithm, step one is to write out the coordinates for the Gauss point. Okay. Okay. And so we can choose to start from any of the Gauss points. So we can, choose any of the ones there. But let's start with the one in the bottom left. Okay. And so in the bottom left, we have xi g is equal to -1/√3. And then eta g is also equal to -1/√3. Okay. And so now that we've established xi g and eta g, we can plug these in to solve for the shape functions and the shape function derivatives. Okay. Okay. Any questions on this so far? Okay. Okay. And so step two, let's compute the shape functions at this Gauss point. Okay. And so basically what we're going to do is we're going to take n1, n2, n3, and n4, okay? And then we're going to plug in -1/√3 for both xi and eta. Okay? And so if we do that, for n1, what we get is 0.622. And for n2, what we get is 1/6. For n3, we get 0.0447. And then for n4, we get 1/6. Okay. Okay. And so the next thing that we have to do is we have to compute all the shape function derivatives. Okay. Okay, so remember there's 8 of these guys. Okay. Okay. And so if we go plug in the numbers, we get -0.394 for dn1 d xi, and for this one we get a positive 0.394. For this one we get 0.106 positive. This we get -0.106. For this guy, we get -0.394. For this one, we get -0.106. This guy, we get 0.106. Okay. This guy, we get 0.394. Okay. Okay. And so those are step 3 and step 4, or step 2 and step 3, sorry. And so remember, these are kind of set up. And so I realize that we're out of time. So, if you guys have to go, definitely, I'm not going to keep you guys. But if you want to stick around for another 5 minutes, I'm going to try to finish up this this example, just so you have kind of a reference for when you start the homework. So, if you have to take off, thank you guys for tuning in as always. Remember, we have a day off on Wednesday, and so I'll see you next Monday. Okay. But if you want to stick around for another 5 minutes, I'm going to finish this example. Okay. Okay. Are there any questions on this so far? Okay. Okay. And so step 4, what we need to do is we need to compute the physical coordinates at the Gauss points. Okay. And so this is going to be, remember, xg and yg. Okay. So remember, the way that we compute this is x1 n1 plus x2 n2 plus x3 n3 plus x4 n4. Okay. And so remember, we computed the shape function values in step 2. And so all we got to do is just plug those in. Okay. So the question is, the initial coordinate values do not contribute in calculating these shape functions. So you're right. So remember, the shape functions are going to be in the parametric coordinates, but the actual physical coordinates of the nodes, or the initial coordinate values, they're going to enter in right here. And so that's what we get: x1, x2, x3, x4. Yeah. So that's where it kind of enters into these ones. Okay, and so we plug all those in, and we get 0.2358 for xg, and then we can do the same thing for yg, and we get yg is 0.228. Okay, and so that's kind of the physical node equivalent for this point right here. Okay. And so with that, that's most of the manual calculations that you kind of have to do. And so from here, it's just going to be a lot of just kind of matrix multiplication. Okay. And so the next step is to compute the Jacobian. Okay. And so all I'm going to do here is just to kind of plug in the values that we have before. Okay. And so first thing is we're going to have a matrix of the shape function derivatives in the parametric coordinates. Okay. And so this, remember, is given in step 3. Okay. And then to that, we're going to multiply a matrix of all the nodal coordinates. Okay. And so just to kind of give you a sense of what I'm computing here, in here, this first matrix is going to be minus 0.394, 0.394, 0.106, minus 0.106. Okay, this will be minus 0.394, minus 0.106, 0.106, and 0.394. Okay, and then here we're going to put in the physical coordinates of all the nodes. So node 1 is, remember, 0, 0. Node 2 is 1, 0.2. Node 3 is 0.8. And what was it? I can't read my own writing. 0.8 and 1. Okay. And then the last node is going to be 0.2 and 0.9. Okay. And so we perform this multiplication, and then we get the Jacobian. And remember, from here we can also compute the Jacobian inverse. We can also compute the determinant of the Jacobian. Okay. All right. Any questions on these? I know I'm going really fast, but I just want to make sure that you guys can kind of see the whole process with some numbers kind of put into these guys. Okay. Okay. And so once we have the Jacobian, the next step is to compute the shape function derivatives in physical space. Okay. And so remember, this is going to be our BG vector. Okay. And so we have everything that we need here, because all we're going to do is we're going to multiply our Jacobian inverse, which we got in step 5. And then to that, we're going to multiply our shape function derivatives in the parametric space. Okay. So remember, this is step 5, and this was step 3. Okay. Right. And so we can plug in the numbers for that. And then step 7, then we just, this is when we bring in our thermal generation. Okay. Okay. And so we have S of xg, yg. Okay. And so this is going to be 20 xg plus 10 yg. And so this is going to be 6.996. Okay. Okay. And so by the end of this, you know, you'll have everything that you need to do, everything that you need from this Gauss point. And so from here, you're going to be ready to move on to the next Gauss point. Okay. Okay. So I ran quite a bit over. So thank you guys for sticking around. I think what I'll do on Monday is I'll kind of revisit this and kind of go through it a little bit more slowly and kind of bring in the Neumann boundary condition term too. But hopefully by this example, you know, this should give you enough to do the homework. Okay. So thank you everybody for sticking around for a little bit extra. You know, I try not to do this most of the time, but you know, I just wanted to make sure that you guys had an example to look at for the homework. Okay. So thank you everybody for tuning in. Remember, Wednesday is a holiday, so we're not gonna have a lecture. And so, you know, if you have questions on the homework, you know, definitely email me, Discord me, you know, anything. And so have a good rest of your week. Have a good weekend, and I'll see you on Monday.
Thank you, Professor.
Thank you. Thanks, Sarah.